Hello everybody, this is Jeff Janess, and in this lecture we're going to discuss several common ways to analyze the shape of the land. All of these methods start with a DEM, or Digital Elevation Model. It's a raster dataset which contains elevation values in the raster cells. This topic is also sometimes referred to as terrain analysis and sometimes geomorphology. Lots of different ways to describe analyzing the shape of the landscape. And in particular, we're going to discuss slope, and we'll discuss a few issues we commonly encounter with slope when we calculate it as a percentage value. We'll also look at aspect and discuss different ways to display and analyze that. Aspect can be a little tricky because it's a circular variable, so that the difference between 1 degree and 2 degrees is the same as the difference between 1 degree and 359 degrees. And this means we have to be careful when we're calculating statistics that would describe mean aspect direction over the landscape. We'll also look at insolation, which is the amount of solar energy that reaches the landscape. We'll look at hillshades. These days, hillshades are usually used more for aesthetic purposes than analytical. Before the insolation tools were available, we would often use the hillshade as sort of a poor man's insolation. And finally, we'll look at several ways to calculate curvature, and we'll discuss the uses of each method. Okay, let's start with slope. I'm sure we all know what slope is. We know why it's important. Many wildlife species seem to select habitat partly based on slope. If you're a timber beast, slope affects what kind of harvesting method you choose, and even whether an area is harvestable or not. If you work in the field for any reason, slope directly affects how difficult the work can be and how tired you are at the end of the day. There are a few things to consider regarding slope, though, and a few things that people often misunderstand. Now, in forestry, we usually measure slope in either percent or degrees, and ArcGIS offers the option for both of these. There are other units of slope that you can use, but since ArcGIS doesn't offer them, we're not going to go into them here. A percent slope is defined as the rise over the run. As we climb a slope, we run forward some distance and we rise up some distance. If we divide the amount we've gone up by the distance we've gone forward, we get percent slope. Now notice that 100% slope only means that we've gone forward by as much as we've climbed. 100% slope does not mean a vertical cliff, and this is a common misconception. A vertical cliff would actually be equivalent to an infinite percent slope, where we would try to divide any distance we've climbed up by a distance forward of 0. So percent slope values range from 0 to infinity. Slope in degrees, on the other hand, ranges from 0 degrees for perfectly flat up to 90 degrees for perfectly vertical. Now notice that a 45-degree slope is equivalent to a 100% slope, where the rise is equal to the run. Now it's not too difficult to convert between these two units, but it does take a little trigonometry. These equations will do it, and they're also in your lecture slide notes if you want to look them up and copy them. Now here's an important issue with slope, and this is when we're calculating with percent slope. We often want to calculate slope statistics. We want to know what the mean and standard deviation of slope is in our study area. But we can't do this if our slope values are in percent. The problem is that percent slope goes from 0 to infinity and rises exponentially as you approach a vertical cliff. Slope in degrees rises in a linear manner as you approach a vertical cliff. And this means that when you calculate a mean from the percent values, your mean will be incorrect and it's going to be higher than the actual average slope in the landscape. And just to give an extreme example, just to illustrate the point, suppose we take two slope values. One is perfectly flat, 0 degrees. Other is a vertical cliff at 90 degrees. Clearly, the average of these two slopes is halfway between them at 45 degrees. The formula for the arithmetic mean confirms this. 0 plus 90 divided by 2 equals 45. However, if we take these same two slope values in percent, well, now we have a 0% for flat and infinite percent for a vertical cliff, and plugging infinity into the equation means that the mean slope is going to be infinity, or a vertical cliff. It's obviously wrong. The average slope of flat ground in a vertical cliff is not another vertical cliff. So, never calculate descriptive statistics from percent slope values. Stats should always be calculated from degrees. If you want to report your slope statistics in units of percent slope, it's still doable. You just need to convert your slope values to degrees before you calculate these statistics. Statistics should be calculated on the slope degree values. Then, later on, you can always convert the final statistics back to units of percent slope for your report. Okay, I think that's a good introduction to slope, so now let's turn to aspect. Aspect is just the direction the landscape's facing, where every raster cell has a value ranging between 0 and 360, reflecting the compass direction. If the landscape's perfectly flat, not facing any direction, then it traditionally gets assigned a value of -1. Now, aspect plays a major role in microclimate, vegetation density, and species composition. It's a major driver of a lot of things we care about in forestry and ecosystem science and management. And in the northern hemisphere, north-facing slopes tend to be cooler and wetter than south-facing slopes. High-elevation plants show up at lower elevations if they're on the north-facing side of a mountain or canyon. And low-elevation plants grow at higher elevations if they're on the north-facing sides, and you get just the opposite pattern in the southern hemisphere. Now, for example, here's a picture of dry lakes just west of Flagstaff, Arizona. In this image, you can see a clear difference in vegetation density on the north and south sides of this ridge. Trees grow denser on the north-facing side. You see a similar pattern here at Fisher Point, just south of Flagstaff. In this image, we're looking directly east at the entrance to Walnut Canyon. So the canyon walls on the right of the image face north, walls on the left face south. So the forest on the north-facing walls on the right is composed of primarily higher elevation mixed conifer forest, while the forests on the south-facing walls on the left are composed of typically lower elevation species like ponderosa pine and pinyon juniper. Now, aspect is an important factor driving a lot of habitat conditions, but it can be a tricky variable to analyze. It's a circular variable, meaning that as you move around the compass, you eventually get back to where you started. The difference between 0 degree and 1 degree is the same as the difference between 0 degrees and 359 degrees. This means that if we want to know the average direction the landscape faces and how much variability there is in direction, we can't rely on the standard formulas for mean and standard deviation. For example, consider a scenario in which we only have two aspect directions. One is 179 degrees, the other is 181 degrees, 1 degree to either side of due south. The arithmetic mean here is 179 plus 181 divided by 2, which gives us 360 over 2 equals 180. And this value is correct. 180 degrees is the mean direction between 179 and 181 degrees. But consider a different scenario. Here we have one aspect value of 359 degrees, the other of 1 degree. Now we're looking at 1 degree on either side of due north. The mean direction here obviously should be north, but the arithmetic mean in this case is 359 plus 1 divided by 2, which again gives us 360 over 2 equals 180 degrees or due south. So in this case, the arithmetic mean of 359 and 1 gave us the exact opposite of the true mean direction of due north. So aspect's tricky, and circular variables often are tricky this way. And this raises the question of what exactly can we do with aspect once we've calculated it? How do we use it in our analysis and management plans? Now, there's a few directions we can take, so to speak. First, while it's true that we can't calculate the normal mean and standard deviation from direction values like aspect, we do have alternative statistics we can calculate that tell us the central tendency and dispersion of aspect values. These are standard formulas you can find in any textbook on circular statistics, and I've also got them included in an appendix in the lab exercise document if you want to copy these out. Also, Esri recently updated the zonal statistics tool so you can use it on circular data. They haven't updated the focal statistics tool for this yet. Now, like most equations, these look a little intimidating and confusing on first glance, and I want to explain what they're doing, though, so you might find them a little more approachable. So let's start with mean direction, and we'll plot a few aspect values to work with. Now, this type of chart allows us to see the distribution of aspect values, or really any kind of directional values. You just draw a compass circle, then draw a line going in the aspect direction for each of the aspect values in your data set. You can plot animal movement directions on this kind of chart too. Now in this example, simple example, we have 4 aspect directions at 45 degrees, 75 degrees, 120 degrees, and 220 degrees. All we have to do to get the mean direction from these 4 bearings is to take the 4 lines and string them together in a path. The mean direction is the direction from the beginning of the path to the end of the path, and that's all that this equation is calculating. Doesn't even matter what order you string the segments together in, the mean direction will always be the same. So what about dispersion? There are two common measures of circular dispersion. Just like normal statistics, both of these circular measures have versions analogous to the traditional standard deviation and the variance. And I took these equations for circular variance and circular standard deviation from both Mardia and Jupp's book, this Directional Statistics, and also Fisher's book, The Statistical Analysis of Circular Data. It's kind of a classic text on circular stats. Now, I took the angular variance and angular deviation from Edouard Bachelet's book, Circular Statistics in Biology. Now, notice that both the circular and angular versions are based on this value R bar, which stands for mean resultant length. The mean resultant length is calculated by dividing the straight line distance from the beginning of the path to the end of the path by the total length of the path. Now, in this scenario, we have 4 aspect bearings. Our total path length is 4. Our straight line distance is 1.92. Therefore, our mean resultant length is 1.92 over 4 equals 0.48. And all of our measures of dispersion are based on this value. Now, think about what this number is telling us. First, it can only range between 0 and 1. If all the aspect values were exactly the same, then when you string them together in a path, it would just be one long straight line. And in that case, the distance from the beginning of the path to the end of the path would be the same as the distance of the path itself. Therefore, this mean resultant length would be the distance divided by itself, which is always equal to 1. A 1 is the maximum possible value for the mean resultant length. Values close to 1 always indicate very little variability in the directions. The opposite extreme happens when you string all the segments together and they end up back where they started. And in this case, the distance between the starting point and the ending point is 0. By dividing 0 by the total length of the path, you always get 0. Now, it'd be reasonable to conclude that values near 0 therefore indicate high dispersion, and it often does mean high dispersion, but here's where circular data can run a little differently than traditional data. There are scenarios where a mean resultant length near 0 are still highly predictable and non-random. Now consider the case of a ridgeline where half the area around it slopes away in one direction, half slopes in exactly the opposite direction. This data set would be composed of a roughly balanced set of opposing directions, and this scenario would produce a mean resultant length near 0, even though there's very little variability in the directions. Or consider a case where an animal roosts in one area and forages in another, and whose majority of travel is just going back and forth. Now, this isn't exactly the same as analyzing aspect values, but it does illustrate this issue when analyzing a similar kind of data. In this case, the connected paths would end up very close to each other, but there's still very little variability in the animal's travel path. So if you have high variability in your direction values, then you should consider this to be a time when you definitely want to look at your data before you start drawing passionate conclusions from your statistics. Now, there's other things we can do with aspect other than calculate circular statistics. Sometimes we don't care so much about the exact direction as much as we care about how it deviates from some particular bearing. This phenomena of north versus south-facing slopes with different microclimates on either side of the canyon or mountain. This is one example. The main driver of the moisture, temperature, and microclimate seems to be how much the landscape direction deviates from north. Deviation of 30 degrees in either direction seems to result in similar microclimate conditions, so we don't really care whether it's facing 30 degrees east or 30 degrees west of due north. It's the 30 degrees deviation that matters. So in this case, it'd make more sense to just transform aspect into a pure deviation from north value. There's a few ways we can do this, by applying trigonometric functions or simple arithmetic functions to the aspect values. If you remember the discussion in our last lecture about applying mathematical functions to rasters, this is another example of that. Trimble and Weitzman, back in 1956, first proposed a method of taking the cosine of aspect. It turns out to directly convert the aspect into a value ranging from -1 to 1. A +1 means that the landscape is facing due north, and -1 means it's facing due south. Values near 0 are balanced between north and south, but there's no indication of whether it's facing east or west. And interestingly, if we take the sine of aspect rather than the cosine, we get a value describing the easterliness or westerliness of the landscape. Sine and cosine basically decompose aspect into the northerliness and easterliness components. Now, Trimble and Weitzman didn't actually take the cosine of aspect directly. They were studying the growth rates of 5 species of oaks in West Virginia and Maryland. They found that these species' growth rates were actually correlated with how much the aspect deviated from a northeast to southwest direction. It wasn't based just on the northerliness versus southerliness. So they calculated the cosine of how much aspect deviated from 45 degrees, which is up in the northeast. So you don't have to calculate the pure northerliness and southerliness if you don't want to. And actually, in 1966, Beers et al. Took Trimble and Weitzman's equation a step further, show a way to apply the transformation to any bearing you think might be important. And if you're interested, I've got both of these papers available for you to look at. There's links to them in the lab exercise document. So you can use any bearing you want as the focal direction, but most of the research I've seen that uses this method, they just calculate deviation from pure and north because so many environmental factors respond to that direction. And just a quick heads up, if you use ArcGIS to calculate cosines of your aspect values or sines, you need to convert the aspect values to radians first. The cosine tool assumes that your data are in radians and not compass degrees. And if you're fuzzy on what a radian is, just remember it's just the distance around the circle that corresponds with the radius of that circle. If you drew a straight line from the center of the circle to the edge, or the radius, then you drape that straight line around the edge of the circle. That would be 1 radian. To go halfway around the circle requires 3.14159 radians, or in other words, pi radians. To go all the way around the circle is 2 pi radians. All right, so now these methods are cool. They're easy to do, but one thing you might consider about this cosine transformation is that the transform values do not have a constant rate of change as you move around the compass. The change of northness that corresponds to 1 degree of change of compass bearing is different depending on what compass bearing you start from. When you move from 90 degrees to 91 degrees, that change in cosine is actually 100 times greater than the change that you get when moving from 0 degree to 1 degree. So we have over 2 orders of magnitude difference in the effect of performing a cosine transformation depending on what aspect values we convert. And this may or may not be a problem for your project, and it's up to you to make that decision. If you like, you can always just take the pure deviation from north in degrees without doing any trigonometric transformations on it, and in this case you end up with a value ranging between 0 and 180, where 0 means it's facing north directly and 180 means it's facing directly south. And of course this method can also be adapted to calculating deviation from any bearing you think is important. One nice thing about both this trigonometric and the arithmetic method is that they both get you away from the circular nature of aspect data, so you don't have to use circular statistics anymore. So now we looked at 2 things you can do with aspect. First, you can use circular stats to describe trends in landscape directly. Second, you can simplify aspect to some basic deviation from some direction you think is important. Now the next method's even simpler. We can just reclassify aspect into categories using the reclassify methods we discussed in the last lecture. Simpler mathematically than any of the other methods we've discussed so far, and it's a good way to determine how much of the landscape generally falls into different categories. If we want to know how much of the landscape is north-facing, and we're not really interested in main directions or variability in directions, then this reclassify method is a good option. By the way, the ArcGIS Pro tool that calculates aspect for you automatically, it symbolizes the raster as if it were a categorical raster. But remember, the actual cell values are direction values, ranging between 0 and 360 degrees, or -1 if the landscape is flat. And before we leave the topic of aspect, I want to quickly show you a cool way to graph aspect data. Most of you are probably familiar with the concept of a histogram. Histograms show you the shape of the distribution of data. The bin heights show you what values are common, what values are rare. In this histogram, we have a relatively large number of aspect values in the 30 to 60 degree range and relatively few around the 240 to 300 degree range. But histograms don't really capture circular distributions very well. The bin at 0 degrees should be right next to the bin at 360 degrees, not on the opposite side of the graph. Therefore, someone, and we'll get to that person in a second, came up with the idea to turn the histogram into a circle. And now we can see how the shape of the distribution extends smoothly across 360 degrees and back to 0 degrees. And it gives a much more intuitive way to visualize the actual direction that most of the aspect data follow. A few of us at NAU School of Forestry are using this type of graph to help us understand bald eagle roosting preferences. These two graphs show aspect statistics for bald eagle sites split into daytime foraging and nighttime roosting locations. Aspect distribution for daytime locations are fairly random, which is not surprising since the eagles are often in flight and would have little reason to position themselves over any particular aspect direction. The nighttime roosting locations are a different story, though. Here, the data clearly show that bald eagles in northern Arizona tend to prefer north or northeast-facing slopes when they roost. Which leads us to trivia time. Who invented this type of graph? This person called this type of graph a rose plot because the bins extend out like petals on a flower. Now, this graph doesn't show aspect exactly, but it does show another circular variable, season, which behaves the same as aspect. They're trying to convince the military command in the Crimean War that the main threat to the troops was disease and poor sanitation, therefore preventable, that the threats were seasonal. The deaths due to combat are represented in red in this graph and are much smaller than the deaths due to disease in gray. This black symbol represents all other causes other than disease and combat. So who invented this type of graph? Yep, it was Florence Nightingale, noted statistician who also did some nursing work on the side. And that wraps up what I want to say about aspect. If you're interested in a more detailed discussion of issues with directional data, then I've included an article I wrote a few years ago on the topic as an appendix in the lab exercise Word document. And this is a good break point for the video, so we'll wrap up this episode here. Now, in the next video, we're going to discuss solar insolation and landscape curvature, both of which are very important drivers of many ecological phenomena, such as vegetation composition, microclimate, stream flow, and exposure to the elements. We're also going to discuss hill shading, which gives you a way of displaying the texture and the shape of the land in your map, so stay tuned for that. And in the meantime, thanks so much for watching. Y'all take care.